Hello my dear students, welcome to my YouTube channel that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is the sp3d hybridization with one lone pair in the main structure. And let's take an example of sulfur tetrafluoride for this case. So today's example is sulfur tetrafluoride. That's SF4. So before doing the hybridization, let's make the Lewis structure of the sulfur tetrafluoride. So I'm writing sulfur over here, one fluorine over here, another fluorine over here, third fluorine over here, and the fourth fluorine over here. Now let's talk about the sulfur. The atomic number of sulfur is 16. So its configuration will be 2, 8, 6. That means sulfur is going to have 6 electrons in its valence shell. Now let's mark that 6 electrons around the sulfur. 1, 2, 3, 4, 5 and 6. Now let's talk about the fluorine. The atomic number of fluorine is 9. So its configuration will be 2, 7. So that means fluorine is going to have 7 electrons in its valence shell. Now let's mark the 7 electrons around all the fluorines. So let's talk about the first fluorine. That's the first electron, second, third, fourth, fifth, sixth and the seventh. Now let's come to the second fluorine. The first electron, second, third, fourth, fifth, sixth, seventh. Now let's talk about the third fluorine. The first electron, second, third, fourth, fifth, sixth and the seventh. Now let's talk about the fourth fluorine. The first electron, second, third, fourth, fifth, sixth and the seventh. Now all the fluorine will be going to make 1-1 bond with the sulfur. So that's the first bond of first fluorine with the sulfur. It's the second bond of second fluorine with the sulfur. That's the third bond of third fluorine with the sulfur. That's the fourth bond of fourth fluorine with the sulfur. Now let's count the number of valence electron for all the fluorine atoms after the formation of 1-1 bond with the sulfur. Let's count the number of electron for the first fluorine. The first electron, second, third, fourth, fifth, sixth, seventh and the 8th. So that means the first fluorine has attained octet, that is 8 electrons in its valence shell after the formation of 1 bond with the sulfur. Now let's talk about the second fluorine. I'm counting the number of electrons for the second fluorine. That's the first electron, second, third, fourth, fifth, sixth, seventh and the 8th. So that means second fluorine has also attained 8 electrons in its valence shell after the formation of bond with the sulfur. Now let's count the number of valence electron for the third fluorine after the formation of 1 bond. So that's the first electron, second, third, fourth, fifth, sixth, seventh and the 8th. So the third fluorine has also attained octet, that is 8 electrons after the formation of 1 bond with the sulfur. Now let's count the number of valence electron for the fourth fluorine. So that's the first electron, second, third, fourth, fifth, sixth, seventh and the 8th. So fourth fluorine has also attained octet, that is 8 electron in its valence shell after the formation of 1 bond with the sulfur. Now let's count the number of valence electrons of sulfur after the formation of 1-1 bond with the 4 fluorines. So that's the first electron, second electron, third electron, fourth electron, fifth electron, sixth electron, seventh electron, 8th electron, 9th electron and the 10th electron. So here sulfur has attained 10 electrons in its valence shell after the formation of 1-1 bond with the 4 fluorine atoms. So that's called expansion of octet, that is having more than 8 electrons in its valence shell after the formation of covalent bonds. So why there is the expansion of octet in case of sulfur? Because we are available with the vacant 3d orbitals in sulfur, which makes sulfur eligible for the expansion of the octet, which we are going to discuss in the hybridization. Now, let's talk about the hybridization now. Here, the central atom is sulfur. Here, central atom is sulfur because sulfur is forming maximum number of bonds, that is 4 bonds. Now let's talk about the electronic configuration of the sulfur. The atomic number of sulfur is 16, so its shell, subshell and orbital configuration will be 3s2, 3p4 and the vacant 3d subshell, that is 3d0. So now let's make the orbital diagram of 3s, 3p and 3d. So in case of 3s subshell, the s subshell has only one orbital, so I have made only one box. In case of 3p, the 3p subshell has in total of 3 orbitals. These orbitals are actually degenerate orbitals. The degenerate orbitals are those orbitals which are having equal energies. So 3p subshell will have 3 orbitals. In case of 3d subshell, we are available with the 5 degenerate orbitals. That is 5 orbitals with equal energies. So that's our 3d, in which we are having total of 5 degenerate orbitals. Now let's fill the electrons according to the electronic configuration. The 3s is having 2 electrons. Let's fill that electrons in case in the first box of 3s. So that's the first electron with the spin of +1/2 and that's the second electron with the spin of -1/2. The 3p is having total of 4 electrons. So we are going to fill that 4 electrons in the 3 degenerate orbitals of 3p according to the Hund's rule. And Hund's rule states that in case of degenerate orbitals, firstly all the orbitals will get 1 electron each. After that pairing will start. So now let's fill the 4 electrons according to the Hund's rule. The first electron in first orbital, second electron in second orbital according to Hund's rule, and then third electron in third orbital according to Hund's rule. Now from fourth electron the pairing will start. So the fourth electron will be here and that will be the pair. This is called the ground state. So this is the ground state of the electronic configuration of sulfur. Now let's come to the Lewis structure. In Lewis structure, the sulfur is forming total of 4 bonds. Here we are having total of 4 covalent bonds. All the bonds are single bonds, which signifies that we are going to have 4 sigma bonds. So in case of sulfur, there must be the presence of 4 atomic orbitals containing 1 electron each, which will make sulfur eligible to overlap with the orbitals of 4 fluorine atoms containing 1 electron each for the formation of 4 sigma bonds. So to have the 4 atomic orbitals containing 1 electron each, we will be going to excite the electron from 3p orbital to the 3d orbital. So let's make the excited state. Firstly, this is the 3s. These are the 3 degenerate orbitals of 3p and these are the 5 degenerate orbitals of 3d. So now let's fill the electrons. The 3s was having 2 electrons. Now 3p is having 3 electrons only. And one of the electron from 3p has excited to the 3d orbital. So 3d is having now 1 electron. So now we can easily observe that now we are available with the 4 atomic orbitals, the 3 orbitals in 3p and the 1 orbital in 3d having 1 electron each. So now sulfur is eligible to form the 4 sigma bonds by head-on overlap with the atomic orbitals of fluorine having 1 electron each. So that's called the excited state. This is our excited state. Now, from here, hybridization will start. Here, there will be the intermixing of the atomic orbitals containing electrons and the atomic orbitals which will be going to form the sigma bonds. So we are in total having the 4 sigma bonds, and the 3s is also having electrons, and in all the hybridization s orbitals are always there. So we are going to mix the atomic orbitals of the third shell, one from the 3s, the 3 orbitals from the 3p, and 1 orbital from the 3d having electrons. So in intermixing process, those atomic orbitals will mix which are having electrons, and that electrons are going to form the sigma bonds with the another atoms. So now here is the intermixing of one s orbital, 3 p orbitals, and 1 d orbitals. So there will be the intermixing process. The intermixing of atomic orbitals is called hybridization. Here there is a mixing of 1s, 3p and the 1d. So total of 5 atomic orbitals are mixing. So we are going to have equal number of new hybrid orbitals, that is 5 new hybrid orbitals. We are going to have 5 new hybrid orbitals come degenerate orbitals, because all the 5 new hybrid orbitals will be of equal energies. So all the new 5 hybrid orbitals will be of equal energies. That's why they are called degenerate orbitals also. So these new 5 hybrid orbitals are over here. I'm making the 5 new boxes, and I have joined them because they are degenerate orbitals. Now, what will be the name of the hybrid orbitals? All the 5 hybrid orbitals will be named as sp3d hybrid orbitals, because it has been formed by the combination of 1s, 3p and the 1d. Second orbital will be also named as sp3d hybrid orbital. Third one is also sp3d hybrid orbital. Fourth one is also sp3d hybrid orbital, and fifth one is also sp3d hybrid orbitals. So in total we got the 5 new hybrid orbitals. All the hybrid orbitals will be named as sp3d hybrid orbitals, and they all are degenerate orbitals, that is orbitals with equal energies. So here we are having 20% s character, comma 60% p character, and 20% d character per hybrid orbital. As it's a mixing of 1s, 3p and the 1d, we are going to have 5 new hybrid orbitals, that's sp3d hybrid orbitals, and all the orbitals will have 20% s character, 60% p character and 20% d character per hybrid orbital. So now let's come to the electrons. In starting, we were having total of 6 electrons. The 2 electrons were in 3s, the 3 electrons were in 3p, and the 1 electron we were having in the 3d. So total of 6 electrons were there. So now let's redistribute that 6 electrons in hybrid orbitals according to the Hund's rule. So that's the first electron, second electron, third electron, fourth electron, fifth electron, and that's the sixth electron. Now, whenever any hybrid orbital is having 2 electrons, then that 2 electrons are termed as lone pair of electrons. So whenever any hybrid orbital is having 2 electrons, so then that 2 electrons will be termed as lone pair of electrons. Let's come to the Lewis structure. In Lewis structure, we were having this to be the lone pair of electrons. This one was lone pair of electrons present in one of the sp3d hybrid orbital. Now let's talk about the fluorine. Fluorine. What's the atomic number of fluorine? That's 9. Its configuration will be 2s2, 2p5. Let's make the orbital diagram for the 2p. In case of p subshell, we are always having 3 degenerate orbitals. Let's fill the 5 electrons over here. 1, 2, 3, 4, 5. So we got the 2p5. Now, in case of 2p5 in fluorine, we are left with one orbital which is having one electron, and that orbital is going to overlap with the hybrid orbitals of the sulfur for the formation of sigma bond. So let's make it over here. That's the 2p of first fluorine. Now it's 2p5. So first electron, second electron, third electron, fourth electron, fifth electron. Here we are left with one orbital. Here we are left with what? One orbital which is having one electron, and this orbital is going to have head-on overlap with the sp3d hybrid orbital of the sulfur for the formation of sigma bond, and that sigma bond will be sigma sp3d p. Why so? Because this sigma bond has been formed by head-on overlap of sp3d hybrid orbital of sulfur with the p orbital of fluorine. Now let's come to the second fluorine. That's the 2p of second fluorine. 2p of second fluorine atom. In second fluorine, in 2p, we are having 5 electrons. So let's make them, well, let's fill them, sorry, with the first electron, second, third, fourth, fifth. Here also we are left with one orbital which is having one electron, which will be going to have head-on overlap with one of the sp3d hybrid orbital of the sulfur for the formation of sigma bond, and again this sigma bond will be sigma sp3d p, because this sigma bond has been formed by head-on overlap of sp3d hybrid orbital of sulfur with the p orbital of second fluorine. Let's come to the third fluorine. That's the 2p of third fluorine. Now again the 2p is having 5 electrons. Let's fill them. The first electron, second electron, third electron, fourth electron, fifth electron. We are left with one orbital which is having one electron, which will be going to have head-on overlap with sp3d hybrid orbital of sulfur for the formation of sigma bond. So again we got the sigma bond sigma sp3d p, because this sigma bond has been formed by head-on overlap of sp3d hybrid orbital of sulfur with the p orbital of fluorine. Now let's come to the fourth fluorine. That's the again 2p of fourth fluorine. Now again the 2p is having 5 electrons. That's the first electron, second electron, third electron, fourth electron, fifth electron. Here we are also having one atomic orbital which is having one electron, which will have head-on overlap with the sp3d hybrid orbital of sulfur for the formation of sigma bond. So again we got the sigma bond, that's sigma sp3dp, which have been formed by head-on overlap of sp3d hybrid orbital of sulfur with the p orbital of fluorine. So that's all about the hybridization. Now let's talk about the structure. We got the sp3d hybridization. For sp3d hybrid orbital, we are having standard structure to be trigonal bipyramidal. But this time we are having one lone pair in one of the hybrid orbitals. So let's make the structure with a lone pair. So that's the sulfur over here. One fluorine atom over here, second fluorine atom over here, and the lone pair will occupy one of the equatorial position. So that's the rule. In case of trigonal bipyramidal geometry, whenever there is a lone pairs, they will always occupy the equatorial position. So that's our trigonal plate. That's our trigonal plate, and it's just an imaginary linkage. These are not the bonds. Now the fourth fluorine is over here. Sorry, third fluorine is over here, and the fourth fluorine is over here. So whenever we have to name the structure, we don't have to consider the lone pair. So this structure will be named as seesaw structure, but not the trigonal bipyramidal. This structure will be named as seesaw structure because one of the equatorial position has been occupied by lone pair. So we are not going to name it to be trigonal bipyramidal. It will be named as seesaw structure for the SF4. Now let's talk about the energy points, which I always talk about at the last. Here two types of energies are consumed. The first one is energy consumed for the excitation of electron from 3p to 3d. So here I am writing consumption of promotional energy. That's energy required for the promotion of electron from 3p to 3d. So here is the consumption of promotional energy, the energy required for the promotion of electron from 3p to 3d. And the another type of energy which is consumed is the energy required for intermixing or intermixing of atomic orbitals, or we can say hybridization. So here is the consumption of hybridization energy. Now here is the formation of 4 new sigma bonds. So I am writing during the formation of 4 new sigma bonds, during the formation of 4 new sigma bonds between hybrid orbitals of sulfur and atomic orbitals of fluorine, there is a release of energy or a liberation of energy. There is release of energy which compensates promotional energy and hybridization energy. As the hybridization energy and promotional energy is compensated during the formation of 4 new sigma bonds between the hybrid orbitals of sulfur and the atomic orbitals of fluorine, the formation of SF4 is practically possible, or we can say chemically feasible, when all the endothermic processes are compensated by the exothermic processes. Here the endothermic processes, promotional energy and hybridization energy, and our exothermic processes, the formation of 4 new sigma bonds. So whenever all the endothermic process. The promotional energy and hybridization energy is compensated by the energy released during the formation of 4 new sigma bonds. The formation of that molecule, that's SF4, is chemically feasible, or we can say practically possible. So that's all about the hybridization, that's sp3d, with one lone pair in the structure. I hope you all understood it. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.